In this video, we're going to be looking at the real number system. Knowing the names of the numbers and the types of numbers will really help you a lot with your number sense. Take a look at this chart. This is an overview of what we're going to be talking about today. Don't worry, you don't have to read all of this and have it memorized. We're going to go through each type of number individually. But this is a helpful overview of what we're going to look at. All of these are real numbers. So rational numbers are real, integers, whole numbers, natural numbers, they're a part of the real number system, and irrational numbers are also a part of the real number system. All of these numbers inside of this pink oval are a part of the real number system. So let's look at each of these individually. First, we're going to talk about the natural numbers. So you're going to type here natural numbers. We'll type the word natural. And the natural numbers are the counting numbers. So let me change the font size. So when you think about the history of numbers and how numbers developed, people started with the counting numbers, just the basics. So, counting how many sheep you have. 1, 2, 3, 4, 5, 6, 7, 8, 50 sheep. I don't know. You just keep on counting. All of these numbers represented right here are all examples of natural numbers. What you want to do is you want to think positively. So these are the positive numbers that do not include decimals or fractions. So it's just very basic, simple, the counting numbers are the natural numbers. This symbol N represents the natural numbers. This is not super important, but it's helpful to know as you go through your math courses that when you see an N like this, it means it's referring to the natural numbers. And then I would like you to add your own examples. I'm going to go down to the drawing tool and you can add your own examples. I'll add a few here. So maybe you'd want to add 4, or maybe 5, or 22. Basically, they're all numbers that are positive. All right, after you've added some examples, let's go ahead and look at the whole numbers. And I'm going to go back to the text box and I'm going to use purple this time. And okay, so the definition that I'm going to use for you guys is the whole numbers are the natural numbers. So all the natural numbers and one extra number, 0. So this is the only thing, 0, that separates the natural numbers from the whole numbers. I mean, the natural numbers and whole numbers are basically the same thing, except for the whole numbers include this concept of 0. This concept of 0 came later. It's a little bit more abstract. People, were counting items that they had, and then they said, all right, well, what about when, maybe I had this many dogs and then I gave away, let's say I had 3 dogs and I gave away 3 dogs. Well, what number could represent the number of dogs that I have now? And that would be 0 dogs. So this came next, this idea of the 0. And so we have this new term, whole numbers. And the symbol for whole numbers is this fancy W over here. So if you see this fancy W, that represents the whole numbers. And I also tried to write the word whole with what I try to make look like a 0. Because I want you to remember that whole numbers, what's different about them is that they include 0, whereas natural numbers do not include 0. It's 1, 2, 3, 4, 5, 6, etc. So now we need to come down here and add our own examples. So I'm going to go to my drawing tool, and then I'm going to use purple again. So I can still add like before. I can add 4, I can add 5, I can add 22, any positive numbers. The only thing that's different from the natural numbers is that the whole numbers also include 0. All right, let's keep moving. So we talked about natural numbers, whole numbers, and now we need to talk about the integers. So I'll go back to the text box, and I'm going to use white so it'll show up, and I'm going to go to the largest font size. So integers. The symbol that represents integers is a Z, And the Z has to do with the word Zahl, which is a German word. So Zahl. And Zahl in German means number. So that is why we use Z for the integers. So when you see this symbol, that represents this type of number, the integers. All right, the definition, integers are let's see if I can fit this, whole numbers. I'll make that a little bit larger. Let's see if that will fit. The whole numbers, and it also includes negative numbers. So far, when we've been talking about natural numbers and whole numbers, we have not included the idea of a negative number. So that was the next development in our number system, is people were starting to think about, well, what if I owe someone money? How could we represent that? And if you owe someone money, or you're thinking about, below sea level, what number would represent below sea level? We can start using these negative numbers to represent some of these other abstract concepts. So here's some examples. Negative 423 is an integer, negative 47, negative 10, negative 3, negative 2, negative 1. And then, of course, all of these are still included. 0, 1, 2, 3, 50, 103, 502, 278. All of these numbers, 0, 1, 2, 3, were the whole numbers. And then let's add some extra examples. So basically any negative number. So maybe negative 1,000, negative 75. So it includes negative numbers. It also includes positive numbers. So you could write positive 75 and positive 1,000. We already have 0 listed. And I want you to also notice that with the integers, we still do not have any decimals or fractions. So no decimals or fractions when it comes to integers. All right, let's keep going. So now we're on to what we call rational numbers. And rational numbers, rational numbers are any number that can be written as a fraction. Any number that can be written as a fraction is a rational number. And we use the word q, and that's because it has to do with the word quotient. Let me go to the drawing tool and show you what I mean. So basically, 2/5 is a rational number because it can be written as a fraction. And then the idea of the quotient remembers the result of a division problem. And look, when you have a ratio or a fraction, this symbol right here, the fraction bar, really means division. And quotient is the result of a division problem. So that's why the Q is used. Q is for quotient. So any number that can be written as a fraction. So let's say you took the number 3. You can write 3 as a fraction by putting it over 1. So it's a rational number. And this will make more sense as we look at some more examples. So let's go ahead and continue on to the examples. How can the number be written as a fraction so that we can see that it is rational? Okay, so first we're going to talk about how can we change a number into fractional form. So first of all, let's say that you had an integer. If you had an integer and you wanted to change this into fractional form, you would put the integer over 1. So let me give you an example. Let's say that you had the integer 5. If you wanted to write 5 as a fraction, you would just put 5 over 1. Or let's say that you wanted to write -2 as a fraction, you would just put -2 over 1. So there's another example. All right, if the decimal expansion reveals a terminating decimal, remember terminating means that the decimal ends. I'll make that a little bit smaller. So terminating means that the decimal ends. So for example, 0.4, okay? And to change 0.4 to a fraction, we would use place value. So 0.4, the place here is the tenths place. So we would write this as a fraction by writing 4/10, and then we can reduce it by dividing the numerator and denominator by 2, and we would end up with 2/5. So that's how you would write 0.4 as a fraction. If the decimal expansion reveals a repeating decimal, so that means that it has a pattern. So it has a pattern that repeats. That's why it's called a repeating decimal. We use our 9 rule. Okay, so let me give you an example. Let's say that we had 0.2 and it was repeating. So that would be 0.2222 and it would never end. Well, if there's one number in that pattern, you would write it over 19. Let me give you another example. Let's say that you had 0.13 repeating. So it would be 0.131313 forever. Then you think about how many numbers are in that pattern before the pattern repeats. Well, it's a 1 and a 3 before the pattern repeats again. So there's 2 numbers in the pattern, so you would put the 13 over 2 9s to change it to a fraction. Now, there is an example, I've showed you this in other videos, where the 9 rule is not going to work, and that's when the pattern doesn't start right away, and we would use the algorithm. But I was trying to keep it simple here. Basically, the main decimals you'll see is you'll see an integer that you put over 1. Sorry, that wasn't a decimal. But the integer you would put over 1 to make it a fraction. And then when you look at the decimals, if it's a terminating decimal, you use place value. If it's a repeating decimal, you use your 9 rule, or you can use the algorithm. Okay, so we're on to some more examples that will make what we're talking about make a little bit more sense. So a rational number is a number that can be written as a fraction. So let's fill it in again. We're trying to remember these definitions. A number that can be written as a fraction. So -423 is an example of a rational number because it can be written as a fraction. -423 is an integer. So to change it to a fraction, I just put a 1 in the denominator. So now it's a fraction. Okay, over here we have a terminating decimal. And if you have a terminating decimal, you use place value to change this to a fraction. So this is the tenths place. So you'd write the 1 over 10. And then I'm just going to put that -57 out in front. So now this is a mixed number. And you can change a mixed number to an improper fraction. All right, -10.12, and the 1, 2 repeats over and over again. 1, 2, 1, 2, 1, 2, 1, 2. So if this is a repeating decimal, then you can use the 9 rule. So the pattern was 2 numbers long, so we would put it over 2 9s. And we're not going to take the time to reduce. I mean, normally we would divide 12 and 99 by 3, but this video will last forever if I reduce each one of these, so we're not going to reduce in this video. All right, let's see if you have this definition memorized. Rational numbers, a number that can be written as a, go ahead and fill it in. So I hope you're typing fraction. And let's take a look at these examples. So -3 is an integer, so to write an integer as a fraction, you just put it over 1. Now this is a terminating decimal, so we use place value to change this to a fraction. So that's the tens place, so I put the 5 over 10. Now, normally we would reduce it, but we're just going to leave that alone. All right, this is an example where we have a repeating decimal, meaning there's a pattern and that pattern continues forever. So 474747 forever. And what you do with that is use the 9 rule. There's 2 numbers in the pattern. So I put those 2 numbers over 99, 2 nines. All right, over here we have a terminating decimal. So the decimal ends. So we use place value. 1, 2, 5. The 5 is in the, let's see, tens, hundreds, thousands place. So we would write 125 over 1,000, which 125 over 1,000 will actually reduce to 1/8. But we'll just leave it like this, 125 over 1,000. We'll flip to the next set of examples. All right, rational numbers, a number that can be written as a fraction. All right, 0 is an example of an integer, so you can write that as a fraction by putting it over 1. 1/2 is already a fraction, so we don't have to change it to a fraction. 1 to write as a fraction, you put it over 1 because it's an integer. 3/2 is already a fraction. And then 2.09, we're going to use place value, so tenths, hundredths. So I place the 9 over 100. So 2 and 9 100ths. I'm showing you that every single one of these examples is a rational number because each of these can be written as a fraction. If you can write them as a fraction, then they're rational numbers because rational numbers can be written as a fraction. All right, next set of examples. Okay, 3 is an integer, so we would write 3 over 1 to change it to a fraction. This is a terminating decimal, so we use place value to change it to a fraction. So this would be 8/10, which you can reduce, but we're going to keep moving on. This is a repeating decimal, so I'm going to write a 10 out in front. And then this one's a little bit strange. The repeating pattern is 047s. There's 3 numbers in the pattern, so you have to put it over 3 nines. But really, it's weird to write 047. Instead, we're going to just change that to 47 over 999. But it has to be over 999 because technically there's really 3 numbers in that pattern. So you need to have 3 nines in the denominator. If you just had 47 over 99, if you type 47 over 99 into your calculator, it would give you this, 474747. But if you were to type in 47 over 999, that's the fraction that would give you 0.47. Okay, let's look at our next example, 24.925. This is a terminating decimal, so we have to use place value. Tenths, hundredths, thousandths. So we would place 925 over 1,000, which I can see can be reduced, but we're going to leave it alone. And I think this is our last set of examples for rational numbers. 50 is an integer. You can write it as a fraction by putting it over 1. This is a repeating decimal. The pattern is 3451, 3451, 3451. So to change that to a fraction, you write 3451, that pattern, over the same number of nines. So if it's a 4-number long pattern, we put 4 nines in the denominator. And then this is already written as a fraction. I mean, technically it's a mixed number, but it contains a fraction. This could be changed to an improper fraction as well. So we know that each of these are rational numbers because they can be written as fractions. Which brings us to irrational numbers. And irrational numbers are numbers that cannot be written as a fraction. So an irrational number is a number that cannot be written as a fraction. And the symbol for this is either P or I. There's not really an agreed upon symbol for irrational numbers. Some teachers will not even introduce a symbol at all for irrational numbers. But I figured I might as well mention it, that sometimes people use P for irrational numbers and sometimes people use I. The decimal expansion for irrational numbers When you look at the decimal does not, it does not terminate, and it does not repeat. Okay, if you said it another way, you could say instead that in irrational number has a decimal that goes on forever and has no repeating pattern. And I'll make that a little bit smaller so that it fits. So let me give you some examples. So I'll go down to the drawing tool, and the first example that I'm going to show you is pi. And pi is equal to 3.1415926, and it goes on forever. So this is an example of an irrational number because there's no pattern and the decimal never ends. It goes on forever. All right, so let's look at another example. Another irrational number would be the square root of 2. If you take the square root of any non-perfect square, you will get an irrational number. We've also talked about this another day. Let me grab a calculator for this. So let's go to the Desmos scientific calculator. And I'm going to type in for you the square root of 2. Oops. I didn't mean to type in the square root of 22. Let's try that again. The square root of 2 is 1.414213562. It almost looks like it's going to have a pattern, and then it doesn't have a pattern. So let's write part of that down. 1.4142, 1.4142, we'll write a few more. 13562. All right, and I'm out of room, so I'm just going to put dot, dot, dot. So it goes on forever. This decimal expansion goes on forever, and there's no pattern. Something like the square root of 25 is not going to be irrational because the square root of 25 equals 5 or negative 5. There's not a decimal on 5 that goes on forever and has no pattern. So if you take the square root of a perfect square, it's not going to be irrational. But if you take the square root of any number that is not a perfect square, then it will be irrational. Let me give you another example. The square root of 75. Let's type that into the calculator and see what we get. So the square root of 75 gives us 8.66025438. So there's not a pattern, and I know the calculator doesn't keep on going and going and going. It's just because it's programmed to not keep going and going and going because it would just fill the screen and it would never be finished. The calculator would never be finished typing this answer. So the calculator has to round. So the square root of 75 is 8.66025. Oops. 8.660254038. Okay. So in summary, I just want you to remember that irrational numbers cannot be written as a fraction. They have decimal expansions that go on forever and have no pattern. If you look at a rational number, it's either going to have a decimal that goes on forever but has a pattern, or it's going to have a terminating decimal, or we can also take any integer and change an integer into a fraction. So hopefully that gave you a good little basic intro into the real number system. All of these numbers are a part of the real number system that we talked about. Rational numbers, integers, whole numbers, natural numbers, irrational numbers, those are all real numbers.